imagine a future where tiny devices move through the human body, monitoring diseases, detecting early warning signs, or even coordinating treatment exactly where it is needed. That vision sounds exciting, but it creates a basic engineering problem. How do such tiny nanodevices communicate and process information at all? At that scale, traditional communication and computing do not really work. A nanodevice might not have an antenna or a digital processor. Instead, it needs to communicate more like cells already do in nature and inside your body, by using molecules. This idea is called molecular communication. But molecular communication is not easy to engineer. Molecule movement is chaotic, constrained, and difficult to control. So the central question of my thesis is this: how can we start turning the messy world of molecules into something more structured and reliable, into something like a communication network? I approached this question on 3 levels. As a communication engineer by training, first I looked at what it takes to set up a network. If multiple nanodevices communicate at the same time, their molecular signals interfere. By deriving mathematical models, we showed that multiple nanodevices can still get their messages across even when they transmit at the same time. And we developed ways to reduce the interference with a simple feedback mechanism. In other words, with the right design, multiple nanodevices can share the same molecular channel. But that only helps if each nanodevice can actually apply some processing to the signals it receives. And a nanodevice might be something like a cell with no way to simply run a program to execute an algorithm. So the next question is, can signal processing happen using chemistry itself? To study that, we turned to simulation of chemical interactions. We demonstrated that chemical reactions can implement important signal processing steps inside a receiver. That means that in the future, some communication algorithms may not need electronics at all. Instead, they could be carried out by interacting molecules. So now we have 2 important pieces: molecular communication between multiple devices, and a way that a tiny receiver nanodevice could process information. But there's still another critical question. If nanodevices release molecules or detect molecules from infections or tumors, how do these molecules actually move through realistic environments, and can that movement be used for meaningful communication? To answer this, we built a simple and accessible experimental platform using low-cost components and different colors of ink as a substitute for different kinds of molecules. We created a testbed that lets us measure and analyze how molecular signals travel through tubes that resemble human blood vessels. This platform has also been recreated by other research groups and is being used as a teaching tool, which shows that these ideas are not only theoretical, but also practically approachable. Of course, we are still far from real medical nanonetworks. This is exactly why interdisciplinary work matters, where my research is going next. Together with biophysicists, we are now trying to implement molecular communication ideas using real DNA strands, which takes us one step closer to reality. So at its core, the pillars of my thesis address molecular communication from theory towards practice: mathematical models for multi-user communication, chemical simulations for nanodevice algorithms, and experiments for realistic molecule transport. This can help lay the groundwork for future networks of tiny devices inside the body that might revolutionize the way we think about healthcare.